Okay, I will continue on and introduce you folks to our next speaker. He is Sebastian Witowski, flying in from Poland. He spent the last weekend in Abu Dhabi and he really enjoyed it. The title of his talk will be Writing Faster Python 3, appropriate with just after Mark's talk. To introduce a bit of the achievements of our next speaker, Sebastian is the lead developer for StatCraft. He's a developer of full stack software like portfolio management platforms or document management systems, and has built systems for companies and institutions such as CERN and MUFJ in Japan, one of the biggest banks. So without further ado, let's give a round of applause for Sebastian.
No, I don't. Okay, let's go. Hi, everyone. My name is Sebastian, and I like to write Python code. I also like to figure out how to make my Python code a bit more efficient. And this Writing Faster Python talk has a special place in my heart because that was the first ever conference talk that I gave 7 years ago. And so yeah, I decided 7 years ago, it's been a long time. It's time to update my talk. Many things has changed in that time. Python 2 is no longer a thing. We have new Python interpreters and initiatives like the one from Mark about making C Python faster. But one thing that has not changed during those 7 years is that whenever there is an internet discussion and two words come up together, Python and performance, there is always someone saying, don't use Python. Python is slow. Python is not slow. Python is slower than other languages, and quite often that's fine. I mean, Python was not optimized for the runtime speed. Python was optimized for the development speed. And comparing the number of Python developers to assembly developers, I think it was a good decision. But why is Python slow? One of the reasons that makes Python slower is also one of the reasons that makes Python so nice and easy to use. Python is a dynamic language, so that combined with weakly typing means that we can use the famous duck typing and we don't have to worry so much about the types of our variables. So nothing stops you from randomly reassigning variables throughout your code. Okay, technically your sanity should stop you from assigning a variable to a string, then to an integer, then to a list, and then to a pandas data frame, but you can do this. And the interpreter has no way to know in advance what's the type of your variable. So it can't do any of those optimizations that statically typed languages can do. For him, your variables are always a mystery. Sure, you declare the string, but what's it going to be 500 lines of code later? Still a string? No one knows. So the thrill of being the C Python interpreter must be crazy. I love those effects. So if you want to learn more about the technical deep dive why Python is slow, there is this really nice talk from Anthony's show that you can find on YouTube. So what can we do about Python being slower than other languages? Well, first of all, I probably don't have to say that in a room full of developers, but I work in various companies. I am still surprised how many of them will pay ridiculous amount of money for their developers just to make them work on some old laptop that was just lying around. Look, if this is your computer, then I'm sorry to break it to you, but Python is not your bottleneck. And hopefully, if you're not programming on a potato, if you have to run some large computations, just rent a server in a cloud. You can also use a different interpreter. When I say Python, I actually mean CPython in my talk. But there are other implementations out there. If CPython is too slow, you can use one of the others, and maybe for your use case, they will be much faster. And one thing that makes Python so great and popular, especially in the data science community, is that Python is a perfect glue code language. It means that you can use Python to orchestrate some libraries that are written in much faster languages. You can use NumPy, which has much more efficient data structures and scientific functions. Or you can use libraries like Numba that has a just-in-time compiler that you can apply with a simple decorator. And again, you will get some really nice speed-up improvements on some mathematical operations and on loops. Yet another way to squeeze those few percent of speed up with almost no cost is to update your Python version. With each new release, various parts of code gets improved. So if you suddenly jump from Python 3.7 to 3.11, it might turn out that your code is much faster now. And even though switching between, let's say, Python 3.9 and 3.10 is not as painful as switching between Python 2 and Python 3, you still need to have a good test suite to make sure that everything works correctly after you update your Python version. But if you do have a good and extensive test suite, then updating Python version is basically a free speed up for your code. And finally, you can write faster Python by using better algorithms and data structures. And that's an advice that applies to pretty much any programming language. Let me show you an example. Let's say I want to compute the sum of powers of the first 1 million numbers. So I can define a total variable here, then create a for loop, go through all those 1 million numbers, add them to the total variable, and print the total. Now I want to check how long it takes to execute this function. I can use IPython and 2 of its magic commands. So I call run to run my example program, and time to time its execution time. This method of measuring the execution time is far from perfect, so in a moment I will show you something much more reliable. But for the sake of this example, let's stick with something simple. And if you have no idea what IPython is, it's a much better interactive shell for Python. So I gave a talk about it. If you're curious, you can find it on YouTube. So back to our example. So I'm running this code, and I can see that it takes 72 milliseconds. And I'm using wall time, which means that I'm starting a timer, running my code, and stopping a timer. Nothing too fancy, but I get a number. Obviously, there is a lot to improve here. So let's start small by moving the total variable inside our function. And once I do that, we are down to 63 milliseconds, which is like a decent 15% of speed up by simply eliminating the need to use a global variable. Global variables not only make your code harder to read and reason about because you have to figure out where you create it, but also what places in your code might be modifying this global variable, but they also make your code slower because it takes time to look them up. But we can do better. We can use the built-in sum function to actually add the numbers. And to make this work, I will switch from the for loop to list comprehension. And as you can see, we are down to 59 milliseconds, which is another few percent of speed up. We can do one more improvement at this point. We can replace the list comprehension with generator expression. And for that, we're just removing the square brackets next to the sum. And now our code is slower. Is it bad? Well, that depends. Optimization is often a trade-off between speed and memory usage. Generator expression has this advantage that it's using less memory because it's only generating the next number when you need it. List comprehension, on the other hand, will generate the whole list at once. So if you're generating a large list, it will eat much more memory, and you might run out of memory. So if you need something much more memory efficient, you can stick with generator expression. We can actually check this with IPython and the memory profiler. So we can see that our list, our list comprehension version is increasing the memory usage by 50 megabytes, but our generator expression has almost no impact on memory. Okay, now we're good. Alternatively, if we can't turn our for loop into nice list comprehension combined with a built-in function, there is another trick that we can use. So we can use this number library and import the just-in-time decorator and just decorate our function with this guy. And by running that, we can see that we are down to 34 milliseconds, which is almost half of the time as it was taking before. So we literally cut down the execution time by half with 2 lines of no-brainer code. And of course, Numba can only improve some specific code, like loops and mathematical operations. So depending on your use case, you might not get such a big improvement. But we can do even better. So if we go back to our version with list comprehension, Python lists are heterogeneous, so it means that you can store different types of values together. But in our example, we are operating on integers, and there is a library much more efficient for working with numbers. As most of you can probably guess, I'm talking about NumPy. So NumPy is packed with functions and data structures optimized for working with numbers, and we can take advantage of that. So we can create an array of integers, and then we can call the power and sum functions from the NumPy library. And if we try to run it, we will improve the execution time by 2 more milliseconds. So, okay, that's not a lot. It's almost like switching to NumPy doesn't make sense. Turns out that the problem is not with NumPy. Problem is with my benchmarking methodology. If I run the benchmarks one more time, you can see that now it takes 10 milliseconds. And that's because my benchmark is also benchmarking the time it takes to run the import statement. And the second time we benchmark it, the import statement is much faster. So that's why I said my benchmarks are terrible, and I'm going to show you something better. But anyway, with NumPy, we got down to 10 milliseconds. So we got down from basically 60 milliseconds to 10 milliseconds, and that's a pretty decent improvement. But I think the most important thing is that we learned some things on the way. We replaced a global variable with a local one, which not only makes our code faster, but also easier to read. We switched to using the built-in sum function instead of reinventing the wheel. You can find a lot of optimized functions that are ready to use in the standard library, especially in modules like iter tools and collections. We used list comprehension instead of a for loop, which is a much more idiomatic way of creating a list in Python. And if you're more concerned about the memory usage than speed, then you can use the generator expression instead. And finally, we reached out for NumPy, which gives you Python bindings for functions and data structures implemented in C and Fortran. So you can keep writing your code in Python, but at the same time, take advantage of those very fast programming languages running under the hood. And we also saw how we can use a just-in-time compiler like Numba, where with just 2 lines of code, we could get a really good speed improvement on our example code. By the way, can we make any of those examples better? Anyone? Can I hear someone shouting a mathematical formula? Yes, we can use a mathematical formula to calculate the sum of powers for the next natural numbers. And if we translate that to Python code, this is how it's going to look like. And if we benchmark that, we can see that we got down to 300 microseconds, which is around 30 times faster than our 10 milliseconds with NumPy. And I'm pretty sure a lot of this time comes from the fact that we are creating variables, creating function, assigning results to a variable, and printing stuff. Fantastic, but the answer is wrong. Python is not very good with a floating point arithmetic. So if we try to cast this value to integer, we see this weird 32 at the end. We could use decimals for better precision, but we know that our division is going to return an integer, so we can just use this integer division, and that's how we're going to get the correct number. And if we benchmark that, we are still sitting at around 300 microseconds, so almost no difference. So what we just did was source code optimization. That is, writing your programs in a way that they will run faster, hopefully without sacrificing the readability. In the rest of this talk, I want to show you some more examples of 2 or more ways of executing the same operation, and then I'm going to show you the benchmarks and discuss why one way might be better than the other. You can find all the examples at this URL. I will show it at the end, so no need to take pictures. That's the setup for my benchmarks. So I used Python 3.10 when I was making the slides. I'm not writing bytecode, so I'm not caching anything. I'm using the standard way of measuring execution time of Python code. So I'm calling the timeit module in the terminal. In the red code, there is some setup code, like import statements and so on, so they won't be part of the benchmark. And in the yellow, I will have the function that I actually want to benchmark. And just for completeness, I have run the benchmarks on this laptop, which is a MacBook Pro from 2021. But it doesn't really matter which laptop I use. You can run the benchmarks on the same computer. You're going to have different numbers. Even if I rerun the benchmarks again, I'm going to get different numbers because I might have some programs using more CPU. And the final values will be different. But what won't change is that my slow examples will always stay slower than the fast examples. OK, let's start with the first example. So let's say you want to do some action, but you are not sure if it's going to work. So there are two common patterns how you can do this. For example, let's say you want to read a file, but maybe the file is not there. So first you check, do I have the file? And then you read it. But maybe you don't have access to read this file. So you add another if statement to check, do I have access to read this file? And then the number of checks keeps growing, and there is still no guarantee that you will be able to read this file because, for example, someone might have deleted the file after the if statement, so you have a race condition and the file doesn't exist by the time you reach this return statement. So instead, you can just try to read the file and wrap everything in a try except block. And if something goes wrong, you catch the exception and you're good. So I was curious which one of those approaches is better. I'm going to use a more simple example. So here I have a base class that has an attribute, and I have a subclass, and then I'm trying to access this base attribute in a subclass. But if you don't have control over the base class, maybe the attribute is not there, so I need to check it. So I try to access the attribute, and in the permission variant, I'm checking if this class has the attribute, then I'm accessing it. And in the forgiveness variant, I am just trying to access my attribute and catching the attribute error. And if I benchmark both of those functions, I can see that asking for permission is around 15% slower. It's not much, but it's a bit slower. What happens if I have more attributes to check? So now I have 3 attributes, same situation. I check for the attribute 3 times. If they are there, then I'm accessing them. Otherwise, I'm just wrapping everything in a try except. I benchmark again, and I can see that now asking for permission is 82% slower. So it's getting slower the more checks I'm doing. So is asking for permission always better choice than asking for forgiveness always a better choice than asking for permission? Well, let's see what happens if the attribute is actually missing. So right now, I commented out one of those attributes, and the rest of the code stays the same. Please stop showing my sidebar. And when I run the benchmarks, now we can see something completely opposite. So asking for forgiveness is now almost 4 times as slow as asking for permission. So the tables have turned because exception handling is expensive. So a good rule of thumb here is to ask yourself, is it more likely that my code will throw an exception or not? If the answer is yes, I will probably get an exception, and you can predict what will go wrong, then an if statement is a good idea. It will be much faster than handling the exception, and it will much better show the intention of your code. But if you find yourself putting a ton of if statements only to catch some errors that happens once in a while, and on top of that your code already broke twice because you forgot about some corner case, then maybe it's better to just run your code and ask for forgiveness. I have to skip some example because I don't have time, so I'm going to skip this one. Let's talk about lists. So let's say I have a list of numbers, 1 million numbers, and I want to filter all the odd numbers. I can write a simple for loop, and that's going to do the job. And for filtering 1 million numbers, that takes 33 milliseconds. But since we are filtering something, there is literally a function called filter in the standard library, so we can maybe use that. And the code is simpler, but it's also slower by around 50%. So instead of using the filter function, we can try to use the list comprehension since we are constructing a list. And the list comprehension is a clear winner here. It is using a for loop is around 30% slower, and using the filter is almost twice as slow as using a simple list comprehension. So in this example, we tried to use 3 different structures, and while the list comprehension was a clear winner in terms of speed, each of those code structures that we use actually has a use case. So list comprehension are the best choice if you want speed when creating a list. But if you don't want to have the whole list at once, then a filter is a very good solution because it will actually return you an iterator. So if we look at the second example, you can see that I'm actually calling list on the results of the filter function, so I get the whole list back at once. And it is this list creation that takes most of the time. So if you need an iterator that will generate you the next number only when you need it, filter is a much better choice. And finally, we have a for loop that, well, some people might call non-Pythonic for creating lists, but there is a limited amount of if statements that you can put inside the list comprehension before it becomes unreadable. So for much more complex filtering, I will just stick with the for loop. This is too long, but a good one. You should see the slides later. This is one that I like. So let's talk about creating dictionaries. There are 2 ways how you can create a dictionary. You can call a dict function, or you can use this curly bracket literal syntax. And in many cases, they are equivalent, so you might not give it much thought and assume that they both take the same amount of time. But actually, if we measure their execution time, we can see that using the dict function is twice as slow as just calling those curly brackets. And that kind of surprised me, so I decided to see what's going on. So I fired up the disassembler for Python bytecode, and I looked what happens when I call each of those functions. So this module that Mark was showing before can be used to show you the bytecode instructions. And even though I usually don't know what most of those means, the interesting one is this call function here that we execute when we call the dict function. You see, nothing stops you from doing that in your code. I mean, it's stupid, but Python allows you to be stupid. So when you call dict, Python interpreter has to check if maybe this function is actually overridden somewhere. But if you just use the curly brackets, this is a Python statement. So there is no way for you to override it, and Python can directly call the corresponding bytecode instructions. So that's why using the literal syntax for creating dictionaries, lists, and tuples is much faster than calling the equivalent function. And this module is a great tool if you want to see what bytecode instructions are actually being executed. So if you're curious how something works, you can check it out. This I have to skip because I have 6 minutes and I want to summarize what we just saw. I also have benchmarked all my examples with different Python versions because I was curious how much faster they get if you upgrade Python version. So I just used pyenv to switch to Python 3.7, run my benchmark, switch to Python 3.8, run my benchmark. And I made this table where I have my functions on the left. On the top, I have different Python versions I use, 3.7, 8, 9, 10, 11. And the last column is the interesting one, because here we can see how much slower was Python 3.7 compared to Python 3.11. And as you can see, switching to Python 3.11 gives us a quite significant speed ups compared to the older version with like some occasional degradation in performance. But usually we get quite a nice speed up after upgrading to Python 3.11. Here's the rest of the benchmarks. You can find the benchmarks in the folder in the repository for this talk. And I have even more examples that didn't even fit on the slides because I had a lot of fun gathering them. So you can find all of them in the repository. I also benchmarked some functions, and the improvement was not in the direction where I would expect it. So you can, so I tried to explain why we didn't get the improvement. And the idea for this presentation started as a list of articles on my blog. So if you want to get more details about everything I showed you today, you can go check it out. And let's jump to conclusions. So source code optimization is often the last thing you will think about when you have performance problems. And that kind of makes sense. I mean, no one is optimizing the code by rewriting it from scratch, except when your code is very bad to start with. But source code optimization is something that you should be doing when you notice not when you notice some performance issues, but it's something that you should keep in the back of your head when you write your code in the first place. Just being curious about what code structure is faster will lead you to understand Python better, understand which data structure is better for a specific scenario, and sometimes even understanding what Python is doing under the hood of your code. So replacing a for loop with a list comprehension is an easy thing to do when you write the code. And even though it might increase the speed of your code by, let's say, 20%, if you replace a for loops here, if you change the data structure there, if you use the built-in function somewhere else, then suddenly your code will be twice as fast. And last but not least, please, please, please don't sacrifice the readability of your code for some small performance gains. Sure, fast code is great, but fast but unreadable code is not great. Thank you very much. Here are all the links. Please keep them on for a few minutes.
Thank you, Sebastian. We might have time for maybe 2 questions. Okay, I'll go behind first. Yeah.
Hi, Sebastian. Great talk.
Thank you.
See, basically, I'm a software developer who is lazy. Okay, and code I work is like mostly like millions of lines of code. So it's very hard for me to go through each and every line of code. Is there any extensions or tools that can analyze the source code and can give me suggestions that can save time?
Yes. There are some, for example, there are some open source plugins for Flake 8 that will give you some hints. There are some commercial solutions. I am actually using one that has a free version for like personal usage. So there are tools like that that will tell you like, hey, this can be a list comprehension, this can be a generator, blah, blah, blah. So there are tools like that. They will work both in your code editor and they can be plugged to your CI. So you can find tools like that.
Okay, it seems that Mark has the same question. So someone has a different question? Yeah, okay, thank you.
Okay. I want to ask you about, is there any situation that we can sacrifice readability or performance?
Yes, C extensions or now Rust extensions. No, I mean, if you have like critical parts of your code, obviously you can rewrite them in a much faster language. I see there is a lot of hype for like implementing critical parts of your software in Rust. So obviously, if you need speed, you might go for a faster language. But like in general, when it comes to like most generic Python code, it's better to stick with readability.
Thank you.
Okay, maybe one more question. One more question. One more question going once. One more question. Okay, there you go.
It's related to general Python web server. Last time when I benchmarked it, it was like 5-6 years back. I was getting around 1,800 or 2,000 requests per second. But so I had to rewrite in C++ where I was getting 75,000 requests per second. So did it get any better?
Again, if you're hitting the limits of Python, there is Elixir and other things that are like optimized towards having like many connections. So again, you need to like evaluate how many requests you're getting, and maybe if you're really reaching the limits of Python and even using the fast API or one of those very fast libraries is not helping you, maybe you have to switch to something else.
Thank you.
Okay, folks, I think that's it. Can we have another round of applause for Sebastian? He'll still be around if you want to catch him in the hallway or ask questions.